Welcome to Hot Chips 34. Keynote 2. Beyond Compute. Enabling AI through system integration.
Hey folks, and welcome back. Welcome to the second Hot Chips keynote. My name is Ron Diamant. I'm the program committee co-chair this year, together with Kirsti Asanovic, and I'm thrilled to introduce the keynote speaker today, Ganesh Venkat. Ganesh is a senior director of hardware engineering at Tesla, where he started the Silicon and Systems Group at 2016. He currently leads the AI hardware efforts and is responsible for the DOJO supercomputer. Ganesh was also responsible for the neural net accelerator on the path-breaking full self-driving computer, which is in production in all Tesla vehicles since 2019. So I have one as well. Prior to Tesla, Ganesh played various crucial leadership roles at AMD for nearly 16 years, spanning the designs of Opteron 64, the pivotal Zen and K12 processors, and a few others. And a fun fact that I learned recently is that one of Ganesh's designed processors also holds a Guinness record for the world's fastest clocked silicon. Ganesh will talk about enabling AI through system integration, and I've been personally waiting to hear this talk. So Ganesh, take it away.
Thank you so much, Ron, for that introduction. Very warm greetings to all of you from wherever you're watching and listening to this talk. I'm missing the regular Hot Chips setup. And since this year it's going to be virtual, I thought, why not change it up a little bit and do a real green screen? This is my green screen in my backyard. Well, it's an absolute honor and privilege to give this keynote for Hot Chips, one of the most premier chip design conferences. I'm excited to talk about how to enable future AI systems through tight integration, which goes well beyond compute. Compute in terms of teraflops and exaflops get the limelight, but an effective system goes well beyond just those compute aspects. And I hope through this talk, you'll appreciate some of those. So let's get started. We know computing is all about processing input data and turning it into useful outputs on the other end. And throughout the history of evolution of computers, this has been the primary objective, but we have used different solutions to perform the same objectives, all the way from the early mechanical computers to the left of the screen, to the latest, greatest digital ones to the right. Their job has been to take input data and turn it into useful outputs. Now, one thing that has been changing drastically is the input data itself. The amount of input data to crunch is just going through the roof. And IDC predicted this about a decade ago, but the reality far outpaces that. And especially given the pandemic-related digital moves that has been happening all across, this trend is not going to stop. And it's not just the volume of data, it's the type of data that is also changing over time. Corporate data is typically the most sticky one to change. It doesn't change that often. And the recent study shows that even the corporate data in the last decade has changed drastically. More than 80% of the corporate data is unstructured in nature right now. And what that means is it requires new types of processing. The traditional methods won't work, and machine learning software 2.0 constructs have to be used to crunch those unstructured data to produce those useful outputs. Now, how about traditional data itself? Well, the most traditional data is weather prediction. After all, the initial computers started to predict tides and ocean routes for intercontinental trade to begin. And for weather prediction, like this paper about climbing down Charney's ladder, machine learning in post-Dennard era for computational climate science. The author has documented the digital part of supercomputing at GFDL, which is Geophysical Fluid Dynamics Lab at NOAA. What you see out here is a log linear chart, compute on the log axis over time. And it's not just the growth of this compute, but the type of architectures that have evolved to do the same job, for doing the same processing. The underlying architectures have evolved over time from scalar to vector to parallel vector to scalable, which is another name for GPUs. And then moving to machine learning now. In fact, the author goes further and says, this is a sea of change, which is only parallel to the von Neumann revolution that happened in the 40s. This is dramatic, this is drastic, that traditional data is seeing advantage of using machine learning techniques. And we see that through all these models, such as the climate AI model for localcast that use machine learning techniques, and they do better than traditional ways of computing this. So you can see new data as well as traditional data, both can use machine learning techniques. And then the most difficult data set for computers, which is real world data. Real world data processing is only feasible through machine learning techniques, be it natural language processing, driving in streets that are made for human vision, to robotics interfacing with everyday environment. All of these are only feasible through machine learning processing. And the machine learning applications, what I showed out here are just a sample set. You can imagine from medical field to industrial, there are so many different applications, and this is only going to explode. Now, if I were to overlay the types of architecture out here in this computing evolution, as well as the data which these computers crunched, the initial computers were nothing but accelerators that accelerated strictly structured inputs. In between is the golden era of compute. Algorithmic computers using codes that we programmed, crunched semi-structured data, and created all those useful outputs. And now is the phase where we're getting into learning computers. These computers can handle structured, unstructured, any form of data with ease. Now, before I go further, let me just define what I mean by AI, ML, and DL. AI is about tasks that require human intelligence level compute in real world setting. Machine learning is a subset of AI where we use data to predict, we use data to train these computers, and then subsequently they predict outputs. Deep learning is further subset of machine learning where a particular type of architecture for neural net, namely deep neural net, is used for doing the same learning processing. Now, recently, I was asked by an old colleague whether we require new compute platforms to do this learning compute. The way I'll describe that is traditional computers are used to input data, and then programmers hand code logic through their programs. Those get fed into these traditional computers, and you get those useful outputs. Learning computers are very different. We just flip these relationships. Input data and desired output is fed into these learning computers, and we get the trained logic. And then the trained logic is used in conjunction with new input data, to create those useful outputs. This is very different from traditional compute. This whole process is called training. And then what you do with trained logic is inference. Training is the most difficult aspect of learning. That's why I'll concentrate the rest of the talk on training only. Now let's take a look at what's been happening in this field with the help of OpenAI researchers who have documented this over time. This is another log linear chart of machine learning compute needs on the vertical axis over time. And what you'll observe clearly is for the longest time, they both tracked Moore's law. Moore's law itself is an exponential, but about a decade ago, it just took off. And there's a huge gap between Moore's law rate of scaling and the needs for these machine learning compute. And AI adept systems are further up there. So then the question is, how do we design these AI systems for the future? So for that, let's briefly take a look at what all are involved in any of these training systems. We need data sets. These are data sets from real world that are curated and made sure they're appropriate. And then powerful models that can crunch those real world data set. And of course, the underlying hardware has to provide compute and scale to crunch those. The way they hang together is researchers define goals, and then they collect data set, they curate it, and the curated data set is iterated over time with models, model architectures change, and then the researchers reach the desired results. But this is an iterative process. And this iterative process also involves high level of human involvement, all the way from curating the data sets to reviewing. Now, just about the data sets, if we look what is involved in labeling these data sets, as you see out here in this picture, just to label a traffic cone, a 2D label of a traffic cone, the contours of the traffic cone have to be strictly followed by the labeler, and then so on and so forth for all the things in the scene out there. Now, this is highly variable. Labeler to labeler will differ, and that causes a lot of issues in training data sets. Now, if you further increase the complexity, and this is what we do 4D labels, which includes space and time. This is extremely involved process in real life and real world data, where we not only do space labeling, but also time for predicting the depths. This is where, even though we automated a lot of labeling, the amount of processing, amount of involvement required to label these 4D data sets is astronomical. And we saw that through both the labeling growth as well as the effort required to label over time. Now, it's not just us. The entire industry does this in a very similar fashion. What you see out here is a framework from Meta AI. It's called the Human AI Loop. They call it HALO. And it involves similar steps: curation using people reviewing it, as well as results from all of the outputs of your models. Now concentrate on this word human. I mean, as long as human is in the AI loop, this whole progress is going to slow down. And there's a historical precedence for it. This is from Jack Copeland's book about Alan Turing's electronic brain, where Alan Turing and other researchers in 1930s observed that computers are slow because humans are involved in feeding the inputs, taking the outputs, feeding it to the next step of inputs, and so on and so forth. And that's what led to this huge invention of programmable computers. These hardware had software to go along with them. So now, what can we do for AI, which is similar? Perhaps AI itself or machine learning itself can come to rescue. Is this a chicken and egg problem? Well, no. In traditional programming, it's called recursion. So how about feeding a scene at the bottom and then subsequently refining your models such that you can spit out a well-labeled scene at the top? This is feasible. It requires offline models. These models will require huge amount of network complexity and hardware resources. How do I know that? Our software team already does this. What you see out here is the flow for getting clips from our fleet using offline models and producing labels on the other end. And in fact, last year, our software team demonstrated this, where we asked our fleet to give low visibility scenarios from all across our test fleet, and we got a lot of them. And these auto labeling models started labeling all of these. And within a week, we labeled and we reused that in training our subsequent models. And this happens day in and day out at Tesla. So this is a form of reducing human involvement in labeling data sets for real life or real world data set. What it requires is more and more machine learning resources. Of course, hardware too, which is great for us hardware folks. Now let's look at the models involved. These models are the neural network models, like right from 3D convolutions to transformer and RNNs. We use these in the vehicles every day, and our offline models are very different in terms of architectures that they use. Now, the research has so many more, like knowledge graphs to transfer learning, all the way to like things like multimodal AI, data-centric AI, and art networks. What this means is our software and hardware capabilities have to be flexible and adaptable such that all these models that are there in research that will enable future AI compute, they can be effectively ported onto our current hardware. So flexibility is key in hardware to enable all of these. Now, if you look at the hardware aspects, what does the hardware aspect look like? Now, I'll go back to the OpenAI chart. The same chart, of course, these researchers were able to run these models. That's how they measured that the complexity involved are there. And in fact, they were AlphaGo related models and programs which exist right now. Now, the reality has also been documented, thankfully, by OpenAI researchers, where Hernandez and al. Documented this over the same period. The compute effective growth, 8x of it came from Moore's law. This is the traditional scaling as hardware engineers are used to. 25x, this is astounding. 25x came from algorithmic efficiency, all those models, things that researchers are changing day in and day out to extract more juice from the same compute. This is 25x came from algorithmic efficiency. And astronomical 37,500x came from scale and more hardware. That means this problem is immensely scalable. Unlike traditional HPC workloads, these workloads are really embarrassingly parallel and scale forever. So for the future compute, these two are very, very important. There's an interplay. Flexibility uses the resources in a better way, and then you can do more things, which requires more scale out. More scale out you have, researchers have more flexibility to do newer models and different models, etc. So there's a big interplay between scale out and flexibility. And these are paramount for our future hardware. And the climb up to this learning has happened with multiple steps, like right from big data revolution that happened in late 2000s to big compute, where we could put a lot of compute in smaller dies and smaller chips. That enabled these big model revolution. And this is the machine learning phase. But to get to AI level compute, we need all those real world data crunching capabilities, all better compute, better scale out, and then better models will result out of all those things. Hopefully a few more steps will get us to AI level compute. Now, if I were to summarize these AI system traits, from flexible compute to handling real world data sets, gigantic models, scale out, real-time performance, this is a requirement, as well as feeding these compute clusters for training. Feeding these scale-out clusters is paramount, otherwise we create artificial bottlenecks. Now let's take a look at how we have been scaling our data centers and the compute involved for machine learning. We traditionally build chips, we put them on packages. Packages go on PCBs and boards, which go into systems. Systems go into racks, and racks form the data center as well as the entire building, etc. These are some of the examples of walking through this hierarchy. Now, a lot of us know this, but we don't realize walking through this hierarchy, we lose immense amount of bandwidth and increase the latency multifold. This is orders of magnitude as you go from chip to package to system. And you can appreciate that by just looking at the pitches involved, let alone the speeds of these interfaces. The pitches involved from chip to package to systems, they vary drastically, and that leads to these orders of magnitude. And not only that, if you walk across the hierarchy and compute, let's say, a 64-bit operation, the amount of energy and power required to do that across the hierarchy, you start paying more and more tax as you walk up the hierarchy. And these scale-out systems do walk up those hierarchies pretty often. Now, the chip design industry has been innovating immensely and trying to mitigate all of this. And that's one of the reasons why you see most of the machine learning and AI chips out there are reticle size. You don't want to cross those hierarchies early for these scale-out applications. And that's why all these are reticle sized dies out there. And then further, we extended by packaging technologies like silicon interposer, EMIB, or MCM. And these are a few of the examples out there where we integrate a little more. But what this causes is an immense growth in power. This is just over a few years, GPU trend for power has grown astronomically. And this is not about wasted power. All this is used power because these applications scale out immensely, remember. I mean, gone are the days of single core to multi-core where we maintained the power reasonably similar. And then came the era of dark compute or dark silicon where we turned off portions of the chip so that we can maintain our power levels. With AI applications, it's immense scale out, and this is the result of that. Every piece of logic in your chip will be used. And what you see out here is exactly that. Now, this leads to another issue, which you can imagine, which is cooling. What you see on the left is a graph of cooling difficulty, which is inverse of thermal resistance. And these are for some of the real parts. I mean, this difficulty for our thermal engineers leads to solutions, which are big, bulky, as you can see on the right side. Our heat sinks and heat solutions are becoming bigger and bigger over time. And what that leads to is our systems also grow. And for similar amount of chips integrated in systems, the system gets pried apart. And that leads to all those taxes and losses that I went through earlier. Now, this amount of power has to be also delivered into a small footprint. And for that, mostly we use lateral power delivery, what you see out there. And what, like, Dennard scaling stopped, but with FinFET, we again started scaling down voltage levels. Along with those power increase, voltages going down, this means an enormous amount of increase in amperes that you have to feed through your PDN networks. And this leads to like bulky solutions, big solutions, as you can see on the right. Amount of footprint required to distribute power and deliver power is way bigger than the chips that they provide power to. And this also pries the system apart. And further, transistors are favored by our technology scaling, and compute is heavily transistor driven. And that leads system asymmetry in terms of rest of the system. You cannot scale with the same kind of transistor densities and scaling. And traditionally, people have been overcoming that by introducing another layer of compute called edge compute. Others call it different kind of computes. But the primary idea is to bring those computes closer to the memory and storage. But this is not that feasible for scale out level computes like AI. Now, all of this, I mean, tax of walking through those hierarchies, etc. What all of this adds up to is it's what we have been using is a discrete and a chip-centric view for solving for AI and machine learning. That leads to enormous amount of value proposition loss through the system. So what we need is a system level view with the whole system in mind to solve it in an integrated fashion. Now, talking about systems, how have our systems been evolving? This is about the CPU side of compute, where we had initially one CPUs, multiple CPUs, then we started interfacing them with different network architectures, top of rack switches, data center switches, etc. And then we started adding accelerators for doing some point tasks like video processing or display and graphics, etc. And then these accelerators started handling more bigger problems. So they started talking to each other peer-to-peer. And then the problem size became even bigger. So then we had switched networks where these accelerators started talking to each other. And you'll see this in any modern day machine learning system. Will be very similar to what you see out here. And then the problem size started growing even more. And so now we introduced another level of switching at the data center level. This is the entire top half replicated into the bottom. Now, don't make the mistake that they are the same. Like many people do that, make that mistake that the characteristics of these are the same. No, these are very different. The top is optimized for traditional HPC CPU-centric compute. The bottom has to be optimized for AI compute. The needs of this are drastically different than the top half. And we see that happening around the industry. Like we see these examples from, let's say, the TPU V4 at the top, where they concentrated on that bottom half, solving those networking for AI accelerators, and they saw 10x improvement out of their compute farm. And I think at Hot Chips, we learn more about NV Switch, which is to the left picture out there. NV Switch is another switch architecture, which is catering to that bottom half. And there are many startups that are putting communication and networking as a primary optimization point. Now, all of these, even though these changes are happening, they are happening at the rate and pace of traditional data center, traditional HPC market. That is the illustrative red curve out there. What we need is an accelerated curve, the green curve out there. We need to accelerate this AI accelerators. How do we do that? And why do we do that? Like, because there are numerous opportunities to do better and quicker. All the way when we have a wider aperture than just looking at chips. We reduce the drag coefficients. There are cleaner abstraction layers. If you can concentrate on the full stack solution, there's a lot more value to be extracted out of these computes. And we started asking very similar questions. And that's what led to, can we do better? What would we do better if we were to do this from first principles? And that's how we started Project Dojo. And Dojo is many things out here. It's a supercomputer, but there are so many underlying technologies. And I'll try to walk you through some of them. We did start by making a chip. We call it the D1 chip. This has 362 teraflops for machine learning compute and packs 50 billion transistors in a miserly 645 millimeter square. If you compare transistors per millimeter square, this is probably at the bleeding edge of anything which exists out there. Now, this was just our starting point. Traditionally, these chips are manufactured in silicon wafers. Then we test and sort them into known good dies, package them, and then put them onto PCB boards and build systems. We also did that for a bring-up package, but we just didn't want to do that for our real system. So we started thinking about how to get rid of these hierarchies that I walked you through. And this is where our partners at TSMC and us worked on a new innovative platform, which is called System on Wafer. This is a fan-out wafer where we can reconstruct known good dies and achieve huge amount of compute integration at very low latency and very high bandwidth, all out here. So this new platform, this new integration allowed us scale out right up front. Like amount of compute integrated here is equivalent to many racks for many other competing solutions out there. Now, in order to integrate this in a 2D plane, we did require other innovations. We had the chip, we had to deliver power and deliver power vertically. So we created a module for power delivery, and we used all the fan-out layers to achieve robust power delivery to our chip. And what we found later when we compared was our lateral delivery versus vertical. Vertical had really good characteristics in terms of impedance, frequency response. And then we started building more and more of our system in a vertical fashion. We are vertically integrated after all. So this vertical integration of the system made our training tile possible. This training tile is unparalleled amount of integration from compute to memory to power delivery to communication without requiring any external switches. Huge amount of compute out here integrated and at a very low energy. Now, what you see out here is me holding our compute tile or our training tile. And what you see in front is a regular PCI card. PCI cards typically integrate one, maybe two processors out there. What you see in nearly 2x the PCI card form factor, we've integrated 25x dies. And each die, remember, packs huge amount of compute compared to anything which exists out there. Now, once we have the compute tile and the training tile, we just started tiling them to make our system. What you'll notice is we could tile this in any direction possible. And that adds a huge amount of flexibility to our compute fabric. We could vary these physical ratios of how much compute to how much interface, etc. And you saw that earlier in our system talk. All of these add to additional flexibility for the system side. So what we did out here is we squashed those hierarchies. We have a chip, we have the training tile, and we could build an entire data center, an entire building out of these training tiles. Well, training tile is just the compute portion. We also need to feed it. And you saw earlier in our system talk, feeding this compute cluster was a primary objective. We designed this from the get-go. We have interface processors with huge amount of shared memory as well as huge bandwidth. We have special NIC cards that process all of the data and provide these speeds and feeds for the compute. Now, just moving back to the old chart that I showed about how traditional accelerators work. Let's put how these accelerators use neural network models. Typically, they try to fit an entire model into each accelerator, replicate it, and then flow the data through each one of them. So the entire model has to fit within an accelerator. And what happens if we have bigger and bigger models for AI compute? We will certainly have bigger models. These accelerators can fall flat because they'll run out of memory. And then either they'll spill to system memory, or other accelerators have local pools of DRAM, which they pull up through other interfaces. Now, all of this, and some may try to integrate the CPU stack with the accelerators and try to bring system memory closer. But all of these leads to either complexity in your software stack or the hardware that you have to integrate together, etc. We thought about this right from the get-go. Our compute tile and each of the die were made for fitting big models. These scale out, especially given model parallel approaches. We can fit huge models with relative ease. Now, this is the power of thinking about the system from a system problem perspective, the entire problem. What you see out here to the right is TPU v4 architecture, where they have pods connected in very similar fashion as you saw with our training tiles and data center networks. These are AI-focused systems that can scale out to a large extent. And now hardware and system is just one component. And this is a funny one, because ever before anything like a software ever existed, this is the first time Alan Turing was working on a machine that could layer software on top. He was worried about programming his machine. In this letter to his NPL director, he expresses that clearly. And do you find, like, most of the folks forget about the software till later on. And this leads to similar issues, like your solutions cannot see the end of the, light of the day till you solve the software portion. And this is where you have to think about programmability and flexibility right from the get-go. And that's what we did. Like, ease of programmability for our software counterparts is paramount when we design these systems. What we designed out here, you saw in our earlier talk, is the best of CPU level flexibility, GPU level throughput for compute, network processing level networking capabilities, and neural network accelerator aspects for accelerating neural network graphs. So all of this while providing flexibility, you gotta make sure it's high performance too and scales out. And of course, software stack relies on hardware to help them out. What we had done was design this for compilers from the get-go, have hardware sync and barrier communication constructs that software doesn't have to onerously worry about, achieve flexibility for neural network acceleration through state machines like what you saw earlier in our list parsers, etc. And then fire and forget communication and so on and so forth. What you see to the left is our software stack. What we did was we used PyTorch. We created an intermediate layer, which helps us parallelize to the scale out hardware beneath it. And underneath, everything is compiled code. We do not have handwritten kernels out here. And this is the only way to create software stacks that are adaptable to all those future workloads. Researchers won't wait for your software folks to write a handwritten kernel for adapting to a new algorithm that they want to run. So that's why this is very, very essential for all these future systems. Software stack opportunities are plenty. Take advantage of these clean abstraction layers. And of course, compilers versus kernels. Just like, I mean, that's an age-old argument, but just like machine learning is a field that was revived. It was a pre-existing field and well-researched, but it was revived with all those big data, big compute, and then big models started fitting into it. Similarly, there were a lot of research on distributed computers that happened in 60s and 70s. And this is a call for action. Just all the researchers out there, perhaps we should take a look at those and see what is more relevant in this day and age for machine learning. Now, what we did beyond compute, I just wanted to summarize, but I ran out of the amount of space out here, and I'm sure I'll run out of an hour if I were to summarize that. We went all the way in, all the way from compute formats to compute to scale out to communication bandwidth and latencies to memory, huge amount of memory, disaggregation, compiler technologies. We have a great distributed compiler, and then networking paradigms and so on and so forth. And that's how we do our exapod builds. These are tightly integrated, as we saw earlier, and yet disaggregated, such that each resources can use the right amount of ratios of compute, memory, IO, etc. Such innovation opportunities exist all across. This is for the entire industry. Like there's so much more to do in terms of architectures for scale out, to integration methods that reduce those taxes, to disaggregation forms that help with system flexibility, to the software sides of abstraction, looking at compilers and enabling new algorithms. Now, from a hardware perspective, the top three are very essential in terms of scale out hardware, which reduces the tax of walking through those hierarchies. And thinking about the whole problem is paramount out here. Now I'll go back to that whole computer evolution chart and overlay this graph that Ray Kurzweil so nicely put. It's about that compute growth over time, but all the way from mechanical computers to the latest, greatest. This is an amazing journey. And you can see those architectures, underlying architectures have kept on evolving. The yearn for coming up with better compute solutions has just adapted to that. And what I've added out here is the thing to the right out there you see in green. Perhaps this next phase is all about system integration, integrated systems rather than integrated chips. For all these computers that the rest of the industry, every one of us are building, I'm reminded of this quote. Alan Turing's quote, from 1940s. The computers that we'll build, we'll learn about their capabilities, and there's nothing stopping them from reaching those AI level capabilities. And hopefully before the seminal paper from Alan Turing in 1936 reaches 100 years, we may have computes that are capable of this level of AI processing. With that, I would like to end this talk, and thank you very much. And I'll be happy to answer your questions.
Ganesh, first of all, thank you very much. It's always great to see these historical views, and especially with a zoom out to look at the entire system and not focus on one part only. So enjoy the talk a lot. There are quite a few questions. The first one that I see here is from Ashutosh Dar from NVIDIA. The question is, will Tesla make Dojo available for non-Tesla users?
Sure. Hey, first of all, thanks for this opportunity. It's great to put this together. To that question, I would just say that we are focused on our internal customers first, and Elon has made it public that over time, we will make this available to researchers. But we don't have a time frame for it right now.
All right. The next question is interesting, kind of forecasting into the future. Cliff Young from Google says, in your scaling components, the scale and dollar investment factor was by far the largest, 37Kx, dwarfing the measly gains from Moore's law and algorithms. How much more scale can we, companies like yours and his, and the society afford? And what happens as we approach the limits of scale?
Sure. I don't know where the limits of scale will be, but all I can say is that scaling is not sustainable for sure. That's one of the reasons why we started Dojo. And the fact is we have to get it more efficient such that we can do similar compute in a lot lower power. So performance per watt will be the only other sustainable way of ensuring we can do those scale-outs in an efficient manner. Now, there's an interplay between those algorithms and scale-out. Like these algorithms have been developed for traditional architectures. And once we have new architectures, newer algorithms will find them to be more fitting. And I hope that whole interplay, which I talked about, plays to the advantage and lowers down all those dollars and amount of hardware required to do the same job much more aggressively than what traditionally has been done.
Could you take us maybe behind the scenes in Tesla, whether algorithms are adjusted to this massively parallelized hardware?
So right now we are in that phase where we have the hardware, we have initial aspects that we are doing right now. We are not going to talk about it right now so that we don't take away anything from our AI Day proceedings.
All right. Question from me. Could you maybe shed a little bit of light on how was the process that eventually led you to decide to build the Dojo supercomputer? What were the thinking behind the scenes?
Well, the history of that is right from my interview with Elon. He asked me, what can you do which is different than CPUs and GPUs for AI? So I feel that the whole team, everyone is still answering that question. I would say we noticed many of these bottlenecks first in the inference side, which is what led us to do FSD computers. And then we started noticing similar scale issues for training. And that's simply how it began. And then knowing your workloads is pretty advantageous for any system builder. So we can optimize our systems catered towards our workloads.
All right. Sohum from UC Berkeley and Qualcomm asks, how is the training tile cooled? Did you use any new technology or innovation to dissipate heat from such a high density compute?
we definitely have a lot of technology out there which is hidden, which I cannot go through because there are some partner IPs involved. But it is kind of, at an infrastructure level, it is nothing different than any other liquid-cooled computer as such. But to increase the efficiency, there are many other aspects that we had to design from scratch.
All right. And you have quite an interesting and unique design with the reconstructed fan-out wafer. Could you talk about your learnings from designing this technology, and how would you compare it to other alternatives?
Well, alternatives, you saw the traditional alternatives out there, which is why we started looking for a platform which can integrate more. We looked around, we looked at all the way from silicon interposer to MCMs to many other technologies. And all of them, in terms of scale out, were like looking at maybe a couple of reticle sizes or a little more than that. So that's where we looked at it as a scale out platform has to be large, as large as possible. And then in terms of our learnings, we have a lot of them. But the key factors for us in choosing this fan-out technology, one, of course, is yield. If you have a scale-out which is concentrated on scale-out platform which is concentrated on making sure yield is perfect, then performance is foremost at that point. So we don't get distracted by yield and focus fully on performance, fully on power efficiencies. And the fan-out wafer is interesting. Like what I look at it in terms of what chip industry is doing is going 3D in many places. They went 2.5D and they go 3D. All of that increases. Already you saw the power density increase, and that increases cooling difficulties at a very minute level. And then once you do that, you fall through a cliff. Like you integrated all of that, and then the next level, it's like climbing up Mount Whitney and then going down to Death Valley and then climbing up again for the next. So all those discontinuities is what we considered when we looked at these scale-out platforms, such that they're as uniform as possible. Of course, there are limits of physics in terms of what you can do, but those were some of the learnings and considerations for us.
Thanks. That actually leads to one of my questions. How did you think about the configurations? Because there's obviously a memory bandwidth, for example, scales linearly, but compute scales quadratically. We had this question in one of the previous talks. How did you think about the optimal configurations for the tile and for the hexapod?
We have taken the best judgment call based on the physical limits, as well as what we know our compiler is capable of with our performance modeling thus far. But we can refine it anytime. Like this system is, as we went through the entire thing, flexibility of configuring it both physically as well as logically was paramount in terms of how to utilize the underlying compute.
And can you talk about how you deal with failures? Because with such a scalable mesh topology, if a single node fails, it could be a problem for communication between other nodes.
Sure. So we do have protections right from ECC to other methods of protection, including retries, etc. In terms of, we make sure our yield is focused on those mesh topology first. We have redundancy there. We can do, as you saw, like we have limited capabilities of rejiggering the traffic. So we use all of those capabilities to overcome any of these failure modes. All
right. Kirsta from UC Berkeley and Sci5, first of all, thank you for the historical context and asked a strategic question. When IBM 650 was released, it represented the first large-scale production computer, so folks who wanted a computer didn't have to build their own. Tesla built their own machine, presumably because they couldn't buy one. Do you think Tesla's continued development of custom machines makes sense, especially given the software development costs, or will it make more business sense to adopt some future standard commercial machine?
Well, ultimately, for a system company, if we are able to solve our system problems, like especially real-world data and real-world AI involved with any platform, that's what we aim for. And doing this in-house is essentially because of the same issues that we are seeing in the commercial solutions out there. The market is moving way more slow, and I understand, like, everyone is optimizing, like, these nodes are becoming way more expensive, and most of the semiconductor, I was in the same side of semiconductor trade-offs where do you take care of a particular customer, or you do, like, I would say, least common denominator solutions where you pick 5 from this customer, 10 features from other, and develop it. But for folks like us who want to push the boundaries of scale, those commercial solutions sometimes fall flat. But this like, our true goal is to solve for performance. It doesn't matter which platform we use.
All right. Karthik from IBM Research asks, why did you restrict the training tile to 25 dice? Would it make sense to go with a larger number of dice?
We started way bigger. Well, there are physical limits on what you could do. Like, the same limits as I spoke about did hit us from various angles, but lesser extent. In some sense, we wanted the best balance between having a platform which is reasonable and not pushing the boundaries right away to pushing the boundaries a little later. What I consider pushing the boundaries is kind of having a seamless set of, rather than 5 by 5, the max amount we can fit will be our next goal.
Maybe let's shift a little bit, shift gears a little bit towards software. So we talked a lot about the system implication, how to build an entire system for AI. What did you learn about targeting the software to that system? Are there any challenges that you think we can improve going forward?
Oh, I mean, right from framework level support, which exists for only commercial platforms which are out there. That's why we had to do the middle layer to to all the way to IR levels and things that are near the hardware. There are many challenges that we learned, and our distributed compiler is amazing. Like, it's a technology, like, this is again, like, a lot of distributed compilers were being talked about in 60s and 70s. Most of the folks shied away. Like, most of our compute is concentrated compute communicating over channels rather than truly distributed. And that's where we learned quite a bit in terms of software technology.
And did you see any complexities in the compiler due to the two-dimensional mesh communication structure, or did that go smoothly?
I mean, there are different aspects. The reason for going for max bandwidth is to avoid all those trade-offs that people hit right away in terms of communication channels. And that's what we learned. We planned for it so that we don't hit those limits right away. Now, as we improve efficiency, we will find newer limits of what is feasible, what is not, and we'll constantly adapt to it. The key thing is it's a very flexible platform. In fact, the CPUs that you saw out there can boot RTOS and do multiple things also.
And one more behind the scenes question. Could you talk about the types of neural networks that Tesla is working on and how they map, how different neural network architectures map to the Dojo system architecture?
Well, I cannot talk to the entire architectures that we use, but the ones that we have our software team has published publicly the transformer RNNs and 3D cons. They are constantly refining it. That was, I would say, that was so last year. A lot of things are changing as we speak, and we try to fast follow all of that.
All right. And to conclude, I have to try, is there a Dojo 2 coming?
Well, we won't sit idle. That's all I can say.
All right. Ganesh, thanks very much. The talk was great. It's great to see the historical view again, and the technology is amazing. We're rooting for you guys.